Thank you for introduction. My name is Yao. Welcome to my presentation about physiological basis for non-invasive skin cancer diagnosis using reflectance. My supervisors are Dr. Maki and Dr. Tano. I'm glad here to introduce my work to you. This is the outline of my today's presentation. I will briefly introduce diffuse reflectance spectroscopy first and how it is applied in skin cancer diagnosis using my Monte Carlo lookup table-based inverse model to do skin cancer diagnosis. So diffuse reflectance spectroscopy has been widely used to measure tissue for decades. We use a fiber probe to shine on tissue. Light is injected into tissue, undergoes scattering and absorption. The collected light is called diffuse reflectance. This setup is simple, but the key is to extract quantitative information about tissue structure, compositions, and biochemical properties of tissue from the measured spectra. The reflectance technique is widely used in biomedical applications such as tissue diagnosis for cervical cancer, breast cancer, lung cancer, oral cancer, brain cancer, and skin cancer. Our group focuses on skin cancer, which is the most common cancer in the US. Last year, there are more than 5 million skin cancer diagnosed, leading to more than 10 million deaths. The key to saving these lives is early detection. As you all know, if skin cancer can be found early, it can be surgically removed easily. Currently, the skin cancer diagnosis is accomplished by visual screening and biopsy. However, the visual screening is not accurate enough. The low specificity leads to many unnecessary biopsies, which wastes lots of time and money. In addition, the discordance rate among pathologists is reported to be 14%. This may be because pathologists make medical decisions according to their experience without quantitative standards. These facts highlight a need of a more efficient skin cancer diagnosis tool, and our answer is using our Monte Carlo lookup table to extract some quantitative physiological parameters from the measured reflectance. So we have a lookup table relating reflectance to scattering and absorption coefficients. Why do you need a lookup table? Why cannot we use diffusion theory here? Because the diffusion theory does not work when the source detect separation is too short. The skin is very thin, and we measure the superficial part of the skin. Thus, we cannot use diffusion theory here. Just for information, the source detect separation of our probe is about 250 micrometers, which is smaller than the mean free path of scattering in tissue. So you need a lookup table to relate reflectance to scattering and absorption coefficients. There are two ways to create a lookup table. In 2008, our group published a paper for the first time to report the lookup table model. We created a lookup table based on experiments. Later on, we developed a Monte Carlo simulation light transport model and get the Monte Carlo lookup table model. Based on the lookup table, we can calculate diffuse reflectance spectra given the scattering and the absorption information about the tissue. And our Monte Carlo lookup table inverse model can extract the following parameters. These parameters are oxygen saturation, hemoglobin concentration, melanin concentration, scattering coefficient, scattering exponent, vessel radius, and beta-carotene concentration. So my work takes advantage of a clinical database we collected previously. In 2014, our group published a paper in which we used the principal component analysis to analyze the clinical data set. In this data set, there are 5 types of skin lesions included. There are melanoma, the BCC and SCC are the most common non-melanoma skin cancers. And AK is a precancerous skin lesion. Pigmented lesion is just a dark brown spot, like moles. We use the principal component to do classifications for these 4 groups. We achieved good sensitivity and specificity using the the principal components, but the principal component analysis does not provide any physiological information about the tissue. To answer this need, I use my Monte Carlo lookup table model to fit the measured reflectance in our clinical database. So this is a typical reflectance fit. The dashed blue line represents the measured reflectance, and the solid red line represents the modeled reflectance. We got good fitting results for all types of lesions and their corresponding normal skin. So you can see the black diamond represents the normal skin, and the red triangle represents the lesion. The fits look good, but how about the extracted parameters? Let's have a look at the scattering coefficient first. So after extracting those physiological parameters, I compared each type of lesion to their corresponding normal skin. When we make measurements on each lesion, we also measure the corresponding normal skin. So here the blue bars represent the lesion, and the red bars represent the normal skin. The stars indicate significant difference. As you can see, for all lesions, our results show the lesions have significantly lower scattering coefficient than their corresponding normal skin. The interpretation can be that collagen breaks down during cancer development, and collagen is the main source of scattering in skin tissue. So this is expected. The skin cancers, melanoma, non-melanoma skin cancers, have lower scattering, and the precancerous AK also has lower scattering. The pigment lesions also has lower scattering. Also, my results show that melanoma and pigment lesions both have significantly higher melanin concentration than their corresponding normal skin. This makes sense because this matches what we see. The melanoma and the pigment lesion are dark or brown spots, they must have higher melanin concentration, right? For the hemoglobin, we see significant higher hemoglobin concentration in melanoma than their corresponding normal. And the similar trend in BCC was the normal. So the higher hemoglobin concentration in skin cancer can be explained by angiogenesis. So as cancer develops, there are more new blood vessels, which results in higher hemoglobin concentration. You may wonder, the pigment lesions are not cancers. Why does it also have higher hemoglobin concentration? I have to admit that that's a hard question for me. But we think the higher hemoglobin concentration in pigment lesion is because the melanin and the hemoglobin have some crosstalks, have some interactions in our model. And we are working on multi-layer lookup table models to remove this crosstalk. Currently, our lookup table model is one layer, and we assume the tissue is homogeneous. This may affect the extracted hemoglobin concentration. But the existing extracted parameters can be used to do classification, as we did in previous PCA analysis. So I used the same data, same logistical regression model, the same leave one out cross-validation to do classifications for these 4 groups. The only difference between the PCA method and my model is the input for the regression model. So the PCA provides the principal components, which we don't know what these components are. And my model provides some physiological parameters, so we know what contributes to the classification result. Our model results are as good as our previous PCA results, or sometimes even better. In addition, using my Monte Carlo lookup table model, we are sure what physiological parameters are used to do these classifications. So we found that scattering usually plays a very important role in those classifications. And for distinguishing the melanoma and the pigment lesion was normal, the melanin has an important role here. But I'm still working on optimizing the diagnosis algorithm here. So my conclusions are, the first point is our Monte Carlo lookup table model can extract physiological parameters from measured reflectance. And the second point is, using these physiological parameters, we can classify different types of skin lesions. Hopefully, in the near future, we can achieve a non-invasive, fast, and accurate skin cancer diagnosis. Just one click, one shine, and then you can know what type of skin lesion it is. So my future work will be to develop the multi-layer lookup table model to extract more accurate physiological parameters. And the second direction is optimizing the diagnosis algorithms using reflectance, fluorescence, and Raman spectra together. There's another presentation from our group. Welcome to come if you are interested. I would like to thanks to my supervisors and my lab mates, and also the dermatologists we cooperate with. And I also thank the CPRIT funding. Last but not least, thank you for listening. I'm happy to take any questions.